Okay. Hello, everyone. Welcome to the second talk in our morning quantum learning session. So today we have Ewin Tang. And Ewin's going to, in this talk, I guess, answer a question that I've been asking myself a lot recently, which is how the heck did we miss the random purification channel? So take it away.
Thanks. OK, so this talk is going to be based on joint work with Angelos, Jack, John, and Mark. We have some forthcoming work, Angelos, Jack, John, and I. And I'll also be mentioning that briefly here. So in this talk, I've done my best to bob and weave around the representation theory. However, there's still a lot of technical nuance. So feel free to ask questions whenever. OK, so first off, what is a purification? As you may know from your quantum information course, if I take a pure state and I throw away part of my pure state, then what I'm left with is a subsystem which can be a mixed state, like it has randomness in it. So if I have some bipartite state on 2 registers and I throw away 1 register, I end up with a mixed state. There is a well-known converse to this, which is that if I have a mixed state on some register, I can view it as a subsystem for a larger pure state. So if I have some mixed state, I can always imagine that there is some pure state out there which matches with my mixed state and makes it pure. And so in particular, what this purification is if I have some register that's some d by d matrix, some d by d density matrix rho, what I can do is I can find some pure state, which is like a vector that's size d squared, where if I trace out the second register of that pure state, I get the original state. So it's like I'm tracing out the purifying register to get the original thing. OK, and just to be very explicit here, if I imagine that I can write a density matrix in terms of its eigendecomposition. So if I have a state with density matrix of this form, here the lambdas are non-negative and the VIs are orthogonal, then a particular purification that I can choose is I can choose this particular ones who have VIs in the first register and then computational basis vectors in the second register. And you can observe that if I take this rho star and I throw out the second register, this is the same as if I had measured the second register and then ignored the information. And you can see from that when I do that, what I get back is the original rho. OK, so now I can define what is a random purification channel. So this is an observation that we made in this paper about conjugate queries. It basically says that there is an efficient circuit which can convert copies of a mixed state to copies of a random purification. OK, so this quantum channel takes in a bunch of identical copies of a state rho. And the output is a bunch of copies of a purification of rho. So the output is not a pure state itself, but you can think about it as an average over these purifications. OK, and if you want to get more explicit, this is an average over purifications. What do I mean by that? Well, I can get to any permutation, any other purification by taking one particular purification and then just rotating the purifying register. And so what I really mean by this is pick your favorite purification, and then what I'm going to give you is this output, which is a randomly rotated purification, where I rotate the purifying register. And you can again see that this thing that it's spitting out is still a purification. So it's just like I got n copies of a purification. So maybe this is a little bit subtle. But the main thing that I'm going to point out here is that all of the copies of the purification that you get, it's all the same purification. It's the same purification n times. OK, and what this allows you to do, also, by the way, just to explain, the pure states here, the mixed states here were in this in the system size of D, and the purifying registers, these purifications are size D squared. But if I want, I can also improve it. If I know that the input pure state, if I know the input mixed state has a rank R, then I can make the purifying register also be size R. So it like scales the way that you expect to with rank. OK. But the reason why you want all of these purifications to be consistent with each other is that then you can use it for reductions. OK? So there's a lot of applications of the random purification channel, and they all take roughly the following form, where I have some algorithm which does something for pure states. So it takes in a bunch of copies of some pure state psi, and does whatever, and then it outputs some information about psi. And the idea is that, OK, maybe this algorithm is like, I want to extend it to an algorithm which works for mixed state inputs as well. Then what I can do is I can take, if I have mixed state inputs, if I have a bunch of copies of some mixed state row, then what I can do is I can then, apply my random purification channel. And what I get is a bunch of copies of a random purification. I feed that random purification into my algorithm. And it'll output some information about this random. It'll output the output for this purification. And then from this output, I can then extract what I want to know about the original state.
So without that, you wouldn't have the guarantee that a mixed state is its original pure states, but you wouldn't have the property that it will be tensor product of the same state.
Yeah. So if I gave the algorithm a bunch of purifications, but they were different purifications, the algorithm would be like, what are you doing? I need the same purification. I need the same pure state for every copy. Right? So the fact that they're consistent over the copies is really critical. OK. So so we first realized that you can do this in the context of tomography. So for tomography, how it works is, well, we have a pure state tomography algorithm. So what a tomography algorithm does is it takes a bunch of copies of some state, and then it outputs a classical description of that state. So if I wanted to know what was on my quantum computer, I could run a tomography algorithm, and it would spit it out. And if I have a pure state tomography algorithm, you can then observe that with the same reduction, I get a mixed state tomography algorithm. I start off with a bunch of copies of my mixed state row. I apply the random purification channel. This gives me a random purification. And when I run the tomography algorithm on the random purification, it'll get me a description of this random, like this classical description of the random purification. Then what I'll do is on my classical computer, I'll compute what you get when you trace out the second register, the purifying register. And the thing that I will get is a description of my original state. OK? And the point here is that if my description was good, it was low error, then when I trace out the second register, the description of the original state is also going to be low error. OK? And so what we've done is we've reduced the problem of mixed state tomography to pure state tomography. And if you just assume the pure state tomography algorithm as a black box, the analysis of this is like a paragraph. And what you end up getting is an algorithm which uses this many samples and has this gate complexity. I won't get into the details of all of these parameters. Here is what they are for those who are interested. The main point is that this is better than all of the previous mixed state tomography algorithms that we had. In fact, it's like sample optimal in every parameter. So it's like fully optimal in all of the parameters. This is like it's like theta of this. OK. Moreover, this poly-n gate complexity is also something that was not known prior. So by my understanding, basically every algorithm that uses kind of entangled measurements, we do not know how to implement those measurements. And it's a bit tricky to actually implement these measurements. And so all of the prior work actually gives actually requires like exponential in D. It's like the naive number of gates that you would need to implement these measurements. But we only need polynomial in n. So instead of needing doubly exponential in the number of qubits, we only need singly exponential in the number of qubits, many gates. OK.
Wait, sorry, does that follow from the pure state? Because I thought the pure state learner was still kind of hard to implement.
Yes, so there is a pure state learner. The Hayashi measurement is like hard to implement. But then there is an algorithm which does unentangled measurements. And so those are like, you just, those you can implement with like a T-design. Yeah. Good question. Any other questions? OK, cool. All right, so in my opinion, maybe the most striking thing about this application is the degree to which it simplifies analyses for tomography. So to prove this statement, like the statement I wrote before, the gate and time complexity, the kinds of things that I need are, well, I need to do the pure state tomography algorithm. This is like, I feel like it's like standard theoretical computer science stuff. It's like a concentration inequality. You maybe need an epsilon net and like a T-design, but these are all like out-of-the-box kind of statements. You just need to apply the relevant. You just need to like pull them in as needed, and there's not that much complication. Moreover, even if I wanted to use, even if I wanted to prove the random purification channel, this requires some representation theory, but not too bad. And this is in contrast to the prior literature, which needs to analyze the representation theory of the unitary group. And as a result, it gets quite complicated. Just as an example, the state of the art before this was a 128-page paper where the authors compared their work on it to the TV show Severance. So yeah, overall, I would say not particularly painless. And so we are able to actually like recover all of the results in this paper using, OK, like what I wrote here plus a little bit more. But I would say significantly less pain. OK. Yeah. So the moral of the story is of this work is that, OK, just shut up and purify. And to expand on this a little bit more, I would say that the benefit of the random purification channel is that you can understand it by like two churches. These are churches that are commonly invoked in quantum information. One of them is the church of the larger Hilbert space, and one of them is the church of the symmetric subspace. OK, so the church of the larger Hilbert space is a term that was coined by John Smolin. And it basically says whenever I want to analyze a mixed state, consider a purification of that mixed state and then analyze that instead. So I saw some very cute slides by Patrick Hayden. As you can see, there's an animation where this mixed state goes into the church and then emerges pure or something. Yeah. So there are many devotees of this church. OK, so the reason is because you want to analyze mixed states because for whatever reason they're much more simple to analyze. OK, there's also the church of the symmetric subspace. This is maybe like a related idea, which is that often when you're analyzing objects in quantum information, you will be tempted to use this like Schur-Weil duality and like start hitting it with representation theory tools. And the point is that often it's like a lot simpler and more explicit if you are able to work with the symmetric subspace only. So the symmetric subspace, I've written it here. It's a subspace that's spanned by tensors of pure states. And often, for a decent number of quantum information applications, you actually only need to work with this and don't need to work with like the really heavy representation theory stuff. OK. And so you can think of the random purification channel as like some kind of syncretic merging into a new religion, where you take your input states, you you pull them into a larger Hilbert space, and then when you pull them into the larger Hilbert space, you're now in the symmetric subspace. Okay, so you get this benefit of now, before I was not in the symmetric subspace, but now my Hilbert space is large, my space is symmetric, everything's glorious. Okay. Okay, and so there's been a lot of follow-up work, which I'll try to survey now. A lot of new converts to this to this religion. So this sun represents today, and these two papers. This is where we introduced the random purification channel, and this one in November is where we show that you could use it to improve mixed state tomography. And here are all of the follow-up works that either use random purification channel in a critical way or are direct follow-ups to this work. You can see that people were very busy over winter break. This was really shocking to me. Haven't seen anything like it. But yeah, just to summarize this set of works, and give some highlights. Before we realized that you could use the random purification channel for mixed state tomography, what we used it for is to show sample to query reductions in quantum algorithms. So sometimes quantum algorithms assume that you have access to a state preparation oracle for a state. And sometimes they assume that you have access to copies of the state. And what we're able to show in our work is that these two notions are related in the sense that the number of copies that I need is bounded by the number of samples that you need. Did I get that? The number of queries. The number of queries that you need. Basically, they're quadratically related. Okay, so there's a lot of works about in one model and then a lot of works in the other model. And it turns out that if you use this reduction, you can kind of like coalesce these two into a bunch of unified kinds of bounds. And this gives you a lot of this kind of gives you a much more tight relationship between the two models. Okay. As for the learning stuff, using random purification, you can get optimal sample complexities, or I guess query complexities for learning general channels, and also for learning Gaussian states in both the bosonic and fermionic settings. And in some forthcoming work, we also give an algorithm an improved algorithm for estimating the spectrum of a mixed state. And the interesting thing about this is that it improves over this Kyle-Werner algorithm. And this has been kind of something I've been working on for a long time now. Yeah, it's kind of an interesting fact that you can actually get this O of D, little O of D squared. Okay. As for the quantum information side, there's a couple interesting things that you can do. One of them is that it immediately gives you kind of generalizations of Ullmann type theorems for different kinds of notions. So like there's this Ullmann theorem which says that which gives you the operational characterization of fidelity in terms of the fidelity of purifications. And using the random purification channel, you can show that this thing holds when I swap out fidelity for other notions. Also, you can get very simple proofs for these kinds of quantum-like estimation tasks. So there's this result known as the Holevo-Kramer-Rao bound. And it's been there's been a lot of work on trying to get estimators which achieve this Holevo-Kramer-Rao bound. And it turns out that these results can be massively simplified if you just purify your states first before applying your estimation. And the simplification is like on a similar order to the tomography simplification. Okay, you might have noticed that there's actually a paper that comes before our random purification channel. So we are, I guess, kind of not the first to give this random purification channel. So there's this result by Ananth and Golden, which gives an approximate version of the random purification channel. So if you want to purify a number of states that's like smaller than poly n or poly d, then this result suffices. And they use it to give some reductions in quantum crypto. OK. Cool. OK, so far I have not discussed how you prove this random purification channel. I am not going to go into detail because there is some representation theory there. What I will say is just that the way you do it is you take its operational interpretation. There is this channel which maps a state to a random purification. And then I just apply representation theory. And then I apply like Schur's lemma and Schur-Weyl duality over and over again. And this will basically give a succinct expression for what this thing does in the Schur-Weyl basis. And then there is a circuit which implements what that thing does in the Schur-Weyl basis. And moreover, what you can do is you can actually get a Krauss representation of these things. And if you don't care about the circuit, then you can actually go between the operational interpretation and this like Krauss representation without too much reference to a Schur basis. But yeah, the proof is fairly it's fairly standard in this domain. So much so that we have like a laundry list of similar results that have existed in prior work. So all of these works, they either have they contain the correct calculations, or they are circuits which are close to the correct circuit, like maybe like off by 1 or 2 gates or something, or 1 or 2 operations. And I think given this, it's kind of striking that we haven't actually discovered this until now. Additionally, like the actual random purification channel is very close to the channel for optimal cloning of pure states, which is like I guess a 30-year-old result. So we've really been like circling around this for a while. In particular, I'll focus on these 3 works because these are kind of ideologically similar to the random purification channel. In particular, this most recent one says basically the following, which is that if I have some kind of property testing problem, so I want to know whether a state rho is in a class or is far from that class, then getting access to a purification is unhelpful. So it says that if I have an algorithm which uses copies of a purification to detect a property of my original state, then I can convert this into an algorithm which does not use the purification at all, and instead just directly uses the copies of the state. So you can see that this is like kind of a hardness reduction or something. It's like a kind of abstract statement on the level of algorithms. And you can see that the random purification channel fits very nicely in here, because what is one possible reason why purifications are unhelpful? Maybe it is because if I have copies of my original state, I can prepare the copies of the purification, right? So this is like an algorithmic reason why this reduction is true. And indeed, if you take this proof and you kind of turn it around and try to go the other way to get an algorithm, you basically get the random purification channel. OK. So now I'll go on. I made my title, How Did We Miss It? So I have to answer the question. So I will go on a brief philosophical digression. We'll get out of this soon, I promise. But OK. I think it's probably maybe somewhat timely to ask, to be prudent about how and interrogate why we might miss something simple in our field. And this result could have been discovered a long time ago. And the question is, why wasn't it? And I think the basic answer is that, well, we did not have the correct intuition to even think of such a statement being true. I'll justify this in the next few slides. And moreover, if you want the correct intuition, this is kind of, the correct intuition is what I think is maybe like a quirk of quantum information. It's something that you might not ever need to encounter or ever have to work with in quantum information. So I'll explain what I mean. So there's a bunch of different kinds of intuition that you can have. So the first is like physical intuition. The physics work on this domain is exclusively no-go results. You know, they say basically that universal purification is impossible, and like worse, it's unphysical. And the reason why is about the geometry of quantum states. It's kind of just like a continuity kind of argument, which is that, you know, suppose we had a channel which mapped a state to a purification of that state. Then what you could do is I could apply it to one state, apply it to another state, and then apply it to the average of the states. But then by linearity, if I apply it to the average of the states, I get the average of the purifications. But then this is not going to be a pure state, so it can't be a purification. Okay. So there's a lot of work on like trying to like make this kind of result more substantial. But this is basically the reason why you might not believe that purification could work. And specifically, this only holds for like deterministic purification, right? So the only reason that you get this no-go result is because I have to map a single state to a single deterministic purification. And then somehow the geometry doesn't work out. But yeah, so you know, if you're reading this like physics literature, maybe you like somehow come away with the conclusion that purification is just not something that you can do. So my background is classical theoretical computer science, and from my perspective, this is like a weird statement just because there's not like a nice classical analog for this statement. So I can apply the random purification channel to a classical classical samples from a distribution. And the thing I will get out is purifications of that distribution. These are like quantum objects. There's not like a classical version of this kind of statement. And so this kind of makes it a weird thing that you might not like immediately get access to if you have this kind of intuition. And as an aside, I will note that like often when you're doing quantum algorithms, you are okay with getting access to a purification instead of getting access to the state. Like, so you might just resolve these kinds of purification questions by saying, okay, just give me access to a purification. So you might not spend too much time thinking about this. I will say that like from a TCS perspective, it is very natural to imagine a reduction from mixed states to pure states. And this is like a very obvious thing to try. But then when you dig into like the literature and you look at the results in this kind of domain, somehow you might come away believing that this kind of statement would be false. And the basic reason is that pure state algorithms and mixed state algorithms look very different. So the set of pure state algorithms, they can be solved in a variety of ways. Some are like more like representation theoretic, using a symmetric subspace. Some actually only require unentangled measurements. But then the mixed state algorithms sort of don't really, they look, it doesn't look like you can take a mixed state algorithm and like the mixed state algorithms that are popularly analyzed and like look at it in a pure state kind of way. Sorry, this is a little bit hand wavy, but a more concrete statement is that actually the algorithms that you get from random purification are not like literally optimal in terms of the like the scaling up to lower order. And because of this, a lot of the strategies for designing algorithms basically start off with saying, okay, what does an optimal algorithm look like? And then it does some representation theory, and then it tries to analyze the behavior of this optimal algorithm. And you're not going to get random purification just from that kind of perspective, from that kind of algorithm design. Okay. So this is my explanation of why it's like kind of an unintuitive statement. Okay. So that begs the question, why did we discover it now? And I'm going to explain that there is like a sequence of existing work, which if I fed it to you in, as like a curated selection, it could lead you to this random purification statement. And this correct perspective has been gaining more in popularity in recent years, and sort of we stumbled across it in the right context. Okay, so for the rest of the talk, I'm going to give a kind of a walk to random purification. But first of all, are there any questions before I do that? Okay, cool. So done with the philosophy. Now I'm going to explain kind of how you might motivate the random purification. And this motivation is based on is like a slight rearranging of the actual way that we came across it. It starts off with trying to think about input models for quantum algorithms. And at the time, we were kind of unsatisfied with the state of the world regarding these input models. It's kind of a very inside baseball kind of question. But some algorithms require state preparation oracles. Some require copies of states. If I have an oracle which is a unitary, some algorithms require controlled U. Some require U inverse. There's also U transposes and conjugates floating around too. And so the question is, are these models related? When do you get speedups? And can you separate these models for concrete and interesting problems? Okay. So with this being your motivation, a first question that you might think of is is this question of whether conditional states are useful. So this is a slightly less common input model, but okay, if I have some state psi, some pure state psi, then I can define a conditional state as being 0, 0 plus 1 psi. So it's kind of like I have a branch that's 0 and I have a branch that's psi. I've added this additional phase here because on the left-hand side, you don't know the phase of psi. You don't know the global phase of psi. And so this is representing that global phase in some sense. Okay, so this is a notion that's actually, I don't know when it was first introduced, but it was discussed in this paper about quantum tomography using state preparation unitaries. They get some tomography results assuming this input model. And so a natural question is okay, well, is this model much stronger than the original, than access to states? How should I weigh the two kinds of input models in my head? And the concrete question is there a problem that I can solve with n copies of a conditional state that I cannot solve with n copies of the original state? Okay. Now, I'm going to represent my discussion on this with these animals, and you, the audience stand-in, might say, okay, obviously conditional states can help. Because you cannot convert states to conditional states, right? And what that means is that this is the same as this physical intuition, where there is no channel that can map copies of map a state to a conditional version of that state, at least not deterministically. And this is via the same kind of linearity type arguments. Okay, so somehow the fact that there is a global phase thing on the left, but the global phase becomes a relative phase. This makes it very unphysical, hard to work with. Okay, moreover, you also know that they help because you need them to detect a global phase. So concretely, you could ask this question of, well, I give you copies of psi. Can I detect whether psi is 0 or minus 0? Right? So I can't solve this with copies of psi because they're indistinguishable in quantum mechanics. But I can solve them with one copy of a conditional state. Right? Just because this global phase becomes a relative phase. And so you might think these are reasons to believe that they can help. But somehow I'm maybe this result is not super satisfying to you. If I have an algorithm that uses conditional states and I want to use that algorithm, often for a state that's as input, a state psi that I want to understand, I don't care about the global phase. So, the fact that they help for detecting the global phase is immaterial to me. So, what happens if I don't care about which conditional state that I want? Okay, And then what you might do is just consider the case of n equals 1. So one copy of a state versus one copy of a conditional state, and then see what happens. OK. And then moreover, because you don't care about which conditional state, you might as well choose an average over conditional states as the thing that you care about. OK, so if I have an algorithm which works for a conditional state, then I can average it over the conditional states, and then it should still work, as long as I don't care about the global phase of psi. OK, so this expression, you can write it out. You can write out in terms of the conditional. You can expand it into the two branches. Then you can distribute it. You get these 4 parts. And you can notice that there are these cross terms. And when I take the expectation over a random theta, these cross terms cancel, because the expectation of eta I theta is 0. OK, so those 2 terms get killed, and then the expectation doesn't do anything for the other 2. And then what you get is this expression, which is a mixture of 0, 0, and 1 psi. And the point is that I can prepare this with 1 copy of psi. What I do is I flip a coin. If it's heads, I prepare 0, 0. If it's tails, I prepare 1 psi. OK, so in this way, I can take a bunch of states. I can convert them all into conditional states, and then I'm happy. But then you might ask, like, OK, well, if I want to apply this for an algorithm, I will need the copies of the conditional state to be consistent, right? So what I really want is I want to convert copies of a state to copies of a conditional state, where the state is consistent across the copies. OK? OK, so then you might go back to the drawing board. OK, try n equals 2. So what happens when you look at 2 conditional states? Well, then you can perform the exact same computation. And the thing that you end up with is this expression right here. Basically, you end up with this state being a mixture of 3 branches. One of them requires 0 copies of psi to prepare. One of them requires 2 copies of psi to prepare. And the middle thing is like a 1 copy thing. This is the only non-trivial one. But the way I can prepare it is I can start with one of these states, like the 0, 0, 1 psi state. And then I can do a kind of a Hadamard control swap Hadamard. And this will and then measure. And then this will give me the state with like constant probability. Sorry for I can explain it more if y'all want. But suffice to say, you can just prepare this efficiently. OK. So that means I can get this like expectation over conditional states for 2 copies. And then the same approach generalizes to n copies. So there's an efficient circuit which will transform n states into n conditional states, but the n conditional states it's like a random conditional state. And the circuit will look something like the following. There's like this gadget, and you iterate the gadget over a bunch of copies of psi. So you start with a bunch of copies of 0 and a bunch of copies of psi, and then you move them over to like get them all in superposition in the appropriate way. And in fact, this result is known. So I think this might be kind of this kind of trick might be somewhat familiar to those in crypto and complexity. In particular, I know these 2 references which do something like this. But basically, what this shows is that because I have this circuit that converts states to conditional states, then for any kind of algorithm which uses conditional states to get some information about it, I can convert it to a state which uses. I can convert it into an algorithm which uses states, right? By just taking my initial states, converting them into random conditional states, applying the algorithm to get the information about the conditional state, and then extracting out the relevant information of psi. OK? And this is fine provided that the algorithm doesn't, in particular, like it's fine if the algorithm is invariant to the theta in the psi. So like if the algorithm is detecting some kind of property which doesn't notice the global phase of psi, then this works. Sorry, I think I have this written down. This works as long as your information is invariant to the phase of the conditional state. Okay, so this means that conditional states, they do help to detect the global phase, but in some sense they only help to detect the global phase. And if you have something invariant, then you don't need the conditional states at all. Okay. Now the next problem that we were presented with was about controlled unitaries. So you could ask the same question, except instead of states, you consider unitaries. So a common thing that you do in algorithms is that you assume access to a controlled unitary instead of access to the unitary itself. So this is this controlled unitary. I've added this phase here again because of like the global phase of the U being undetectable. But I could imagine like then asking, is there a difference between getting access to the unitary versus the controlled unitary? That is there something that you can do with queries to a controlled unitary that you cannot do with queries to the unitary? Okay, and then you could have a similar discussion, which is that, okay, you do know that controlled queries help. One reason why is that there are no-go theorems saying that you cannot convert a unitary to a controlled unitary. These are examples of like no-go theorems. Moreover, you do need controlled U to detect a global phase. Right? So if I want to detect whether U is the identity or minus the identity, then I cannot detect that with queries to U, but I can detect that with one query to the controlled U. But then I might still be unsatisfied and say like, okay, I don't usually care about global phase. If I want to, let's say, perform like a unitary tomography or something, then I don't care about the global phase of U for my purposes. And so what happens if I don't care about the controlled U that I want? Or what if I need, what if I'm OK with any controlled U? Yeah.
I guess the example that comes to mind here is like phase estimation, right?
Mm-hmm.
Which does that break here because you end up with a random phase, or is it OK?
For phase estimation, right? So phase estimation, yeah, that is a classic case of you need a controlled unitary, and you need a controlled unitary to get these like the eigenvalues. You could so this you do need a controlled unitary, but if I ask instead like the question of I want to understand, let's say, like eigenvalue gaps or something, like relative differences, or let's say I want to perform some kind of, I want to estimate the eigenvalues, but I'm allowed to rotate it by a random phase. These kinds of things no longer require you to, they no longer require like a reference phase. And so then you don't need the controlled unitary. Yeah. Good question. Okay, so then you could perform the exact same analysis. Consider like an algorithm which queries does one controlled unitary query. And then I consider the output averaged over the global phase in the unitary. Because I don't care which controlled unitary I get. Then if you work out this computation, you can see that it's equivalent to measuring your control register and then classically conditioning, doing a classically conditioned unitary on your original register. And this is because like the averaging in the U decoheres the 0 and 1 branch. Okay, and if you don't like classical conditioning, there's this additional gadget that will also do this for you. It's like this addition thing and like some controlled swap. And then you could then ask like, okay, now can I generalize this to n? And it turns out that if I take this gadget and just do this gadget whenever I want to apply this controlled unitary, with this, the same two registers here, then this actually generalizes to n queries. So the statement that you get is that there is a way to transform a circuit which uses a controlled query, but like a random controlled query, to a circuit which uses just the unitary, just the regular query. And if you turn it around, the way that you can think about this is you are converting queries to U to queries to controlled U. But the queries are over a random controlled U. Now this is also existing in the prior work. It is in an appendix, which I think is not. I think it's buried in this appendix of this Shred and Malsav and Mosca paper. I don't think many people were aware of it before we came across it. But it's slightly different from this. It doesn't use a uniformly random controlled query, but the upshot is the same, which is that if you don't care about the phase of the controlled query, then controlled queries don't help. Okay. Now finally, we return to our purification question, right? And in our current lens of the way that we would ask the question about these purifications is, can I do something with purifications that I cannot do with regular copies? And then from here, you do have all the same kinds of objections. Deterministic purification is impossible. Specific purifications can help, but and you do have these statements that say that purification does not help for learning problems. So it's kind of the shape is very similar to the shape of the previous things. And so even though there's already these statements which say that purification does not help for access to purifications doesn't help, you might expect this stronger kind of statement which says that I can convert states to purifications. Yeah, this is we refer to this intuition as the acorn trick in our paper. Okay. And the final thing to cement your belief in the statement is that you want to convince yourself that you can convert one state to one purification. Okay. And the way that you can do this is I can write my random purification in the way that I said before, which is I apply a hard random unitary to my purifying register of a particular specified purification. Now, because I'm twirling over this purifying register, this is going to be the same as if I just threw away the second register and replaced it with maximally mixed. So what I get is this, I trash the register and then I replace it with maximally mixed. But when I trash the purifying register of my state of my purification, what I get back is a row. And so I can prepare this random purification just by taking my original state and tensoring on the maximally mixed state. And from this computation, it's not at all clear that this is interesting at all. I'm taking a state, I'm tensoring it with maximally mixed state. What have I done? But with the intuition, you can then convince yourself that you can get an interesting statement if I take n copies of the state and n copies of the purification. Okay. Okay. So yeah. So just to make concrete this organizing principle. The idea is that if I have two quantum resources, sometimes it might look like you cannot convert one copy. You cannot strengthen the weak resource into the strong resource. And the reason it might not look like you can do it is because of issues when you try to do it deterministically. But then you have to believe that this is just an issue with quantum mechanics, and that if I consider a random resource, then I can do it. And if you can convert one copy of your weaker resource to the stronger resource, but it's like a random stronger resource, then this should give you some belief that you can convert n copies of the weaker resource to n copies of the stronger resource. And the important thing is that the copies are consistent. So the resource choice is consistent among the copies. And this means that these like weaker and stronger resources are equivalent. Yeah.
I'm confused about the last
Mm-hmm.
Like, okay, I'm not sure I'm following this thing, but if you just want to do this purification for one state, it's trivial, right? Because like you don't have this thing that the state should be the same. Right? So like you start with a mixed state, it's a distribution of the cube, right? So even without anything. So it seems that what's a stronger object here? I guess I'm not sure.
Oh, okay. Yeah, that's true. That yeah, there are multiple ways to take one copy of a state and then write it as pure states, write it as a mixture over pure states. I think the point here is that these states, you can actually reference them as purifications, right? So like if I take a mixed state and decompose it into its eigenvectors, then each individual eigenvector is not going to be a purification of the original state, right? So, and that might be relevant to the algorithm that's going downstream. Does that make sense? Like I think the point here is that I want it really to be this particular form of like a random purification. And if you just consider like, can I express these things in terms of, you could go the route of like, can I express these tensor products in terms of elements of the symmetric subspace? But then when you do that, you will need to lift to a higher dimension at some point. And so like the thing that works for one copy will not work for more than one copy. Does that make sense? Okay. 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 So, you know, this is like a trick that I think should be in everyone's toolkit. So I'll give a little bit more on more detail on what we know about it. So as I mentioned before, these kinds of strategies are able to convert states to controlled states, unitaries to controlled unitaries, states to their purifications. Subsequent to our work, there's been a lot of follow-up work giving crazier versions of these. So one thing that we conjectured is that you could convert queries to a channel to queries of a Stein spring dilation of that channel. This is like a channel version of the purification statement. People quickly figured out that you could do it in parallel. But if you wanted to sequentially query channels and like replace that, or sequentially query dilations and then replace that with queries to a channel, you cannot do that, which I find kind of sad. But yeah, it's pretty cool. And then the same group also gave a conversion of superchannels to dilations of superchannels. Don't ask me what that means. They call it a super channel, which I think is fun. Okay, there's also work by Nora and Angus about converting states which are low rank into compressions of those states. So like putting them down into a lower dimensional subspace. This has some interesting learning applications. You can convert Ds to Rs, basically. And as I mentioned before, there is this application of relating states to their state preparation oracles. And there's still one thing that I think is interesting and I don't know about yet, which is the generalization of this thing, of this state thing to the unitary setting, which is basically, can I take queries to a completion? Like, can completions of isometries help you in a quantum circuit? This, I don't know, but I hope to be true, or that they don't help. I hope that this you can say something there. Okay. But yeah, so what's the moral of the story? Basically, I think the thing that's interesting is that the kind of perspective that we needed were very simple and very 101 kind of perspective shifts that you take. So like the primary thing that we needed to do is we needed to, when we were looking at these access models, insist on providing like operational separations, like separations for a particular downstream problem for these kinds of access models. This is very, very standard in complexity, but it was not super standard for analyses of like unitary oracles and things like this. And I had not really appreciated the strength of this observation. You learn it in like the undergrad class, but it turns out like it actually is really good to think about things in this way. And the second perspective is this one that's becoming been very popularized in quantum cryptography, which is taking these random quantum objects and trying to find combinatorial interpretations of these things. It's like compressed oracle type stuff. And it turns out it may not be clear a priori why the combinatorial interpretation or why this compressed interpretation benefits you, but it turns out to just benefit you a lot. OK, thanks.
We have time for a few questions.
I mean, this isn't like a particularly technical one, but when you were talking about the acorn trick, was this something like, is this like unknown mathy thing, or is it like actually just like did you actually like read the weather paper and like, yes, I can apply this to math, or?
You're asking why we called it the acorn trick?
Yeah, was it actually just based on that paper, or?
Oh, it's because, yeah, this is a good question. The reason why we call it the acorn trick is acorns have this property where they drop their seeds on a cycle, like every so often. And the interesting property of these trees, it's not like oak trees are not the only one that have this property, but they have a cycle, and the cycle is consistent across a region. So you'll have a year which is a mast year, and on the mast year, all of the acorns drop. And the evolutionary reason for this is apparently not super clear. But it was like evocative of you taking these controlled unitaries and then like lifting them into a way that's like consistent across the queries or something. But apart from that, we were not inspired by biology. Yeah. Yeah.
So I understood it's very simple, but I still don't understand how you do it. How do you do it? Can you maybe show 2 copies of row, I don't know, of a single qubit row and show how you actually, what's the algorithm? What's the circuit?
That's a good question. I may not be able to do it off the top of my head. John, can you do it?
2 copies are doable, but very annoying on the fly. But offline, we could probably do it.
Okay.
Yeah,
There's a little bit of bookkeeping that's hard to do, I think, on a whiteboard.
Yeah, it's like slightly annoying. You get you have you do either like a swap or you don't do a swap, and then there's like associated probabilities or something with the 2 cases.
But it does wind up not being too hard. You just measure to see if you're in the symmetric or anti-symmetric subspace. Then there's another simple operation and you're done.
Mm-hmm.
Yeah. Yeah. Sorry, yeah, we can talk about it offline. Yeah.
I have a question.
Mm-hmm.
Is there any hope for reducing Lindbladian learning to Hamiltonian learning? Given that the Lindbladian, the Hamiltonian is purification of Lindbladian. I don't know what these words mean.
That's a good question. We have discussed this. It seems like the answer.
Great, thank you very much.
The naive answer is no, because basically, if you try to purify Lindbladian, the thing that you will get is not if I try to purify like a small time evolution of a Lindbladian, the thing I might get could be like effectively a very large evolution. Like in some sense, like when you purify, it does not retain the property that you're close to the identity. It's somehow like, because you're relying on these averaging over unitaries or something, you get moved very far. So in particular, like Hamiltonian kind of questions seem not super amenable to this kind of stuff.
Can you say more about the this no-go result on testing? Like, are there any situations where you could hope to use purification for getting simpler testing algorithms? Because a lot of those seems to still require wild stuff.
To use purifications to get testing. I think if you want to, so there is this result here about exponential separations between quantum learning with and without purification. But because of these like random purification channel type results, I think what they end up having to do is they end up having to like work in like a low space setting and a low rank setting or something. The basic idea is that maybe if I have a purification, what I can do is I can throw away, like if I have a low rank state and I have a low rank purification, I can maybe throw away the original register and just work on the smaller subspace. But I don't know if there's anything like super convincing in that direction. Yeah.
All right, maybe we can take any further questions offline. So let's thank the speaker.